Okay, yep. Right, so we say that exothermic reactions, they are basically those reactions that give out energy, or you could say that release energy. And then endothermic, it's basically the opposite of that. Endothermic reactions are basically those reactions that take in energy or they absorb energy. And one good way of memorizing this is that exo matches with exit as well. So this is sort of that energy is exiting or the energy that is being released. So for example, let's say we have a reaction that is happening, let's say in this conical flask. If this reaction is exothermic, that means it's going to give out energy like this. If it releases the energy, and when we say energy in this context, we're talking about heat energy. So when heat energy is given out, what's going to happen is that the temperature of the surroundings, it's basically going to increase. So another way to define exothermic reactions are that we say that the temperature, it basically increases. And then endothermic reactions, they absorb energy. So for example, again, let's take a conical flask. A reaction is happening in this context. In endothermic reaction, energy is being absorbed. If energy is being absorbed, that means that the temperature of the surrounding, that is basically going to drop. So another way that we can use to define endothermic reaction is saying that the temperature, it basically decreases or drops in endothermic reaction. Right, is this clear?
Yeah.
Okay. So endothermic and exothermic reactions, they are as easy as this. You just need to know what does each of them mean. Now, the next thing is we use some diagrams that are called the reaction profile diagrams, and we use this to basically show the relative energies of the reactants and the products and what exactly is basically happening as an endothermic or an exothermic reaction progresses from, let's say, to the from the reactants to the products. In order to understand the reaction profile diagram, let's first discuss two more concepts, that is basically activation energy, and then the other thing is it's called collision theory. It will make it easier to understand the reaction profile diagram. Let's first start with the collision theory. The collision theory, it basically says that for a reaction to take place, if we want a reaction to take place successfully, for a reaction to happen, there needs to be successful collisions to happen among the particles. Now, what do we mean by successful collisions and what exactly is happening? Basically, let's say, for example, we have a reaction in which A plus B is reacting to form, let's say, AB. In this case, A and B are the reactants, AB, they are the products, right? So, what's going to happen is that these two reactants, A and B, their particles, during a reaction, when we start the reaction, the particles, they are going to come close to one another. As they come close to one another, they collide with one another. And now, if after the collisions the particles have enough energy, they are going to combine with one another and they're going to form a new product, which in this case will be AB. So you have A and B colliding with one another. If they have sufficient energy, they're going to form the new product AB. But let's say what happens in the case when they don't have enough energy. The particles are coming close to one another. As they come close to one another, they collide. But when they collide, because they don't have enough energy, they are going to bounce back. So we say that because they don't have sufficient energy, they are going to bounce back, and once they bounce back, no new product is formed. So we don't have any new product in this case. Now, the first one, because a new product is formed in this is basically an example of a successful reaction or a reaction. But the second one, in which the particles don't have enough energy, this is not a reaction that is happening. So the reaction fails. Now, the next question is, when we say particles have enough energy and particles don't have sufficient energy, how do we know what is enough for a particle? Basically, that's when the activation energy comes in. Now, activation energy, as the term itself indicates, it's the energy that is needed to activate a reaction. And in simple words, we say that it is the minimum amount of energy that is required by the particles to have in order to basically for a reaction to happen, or you could say for successful collisions to happen if you want to be a bit more specific. So for successful collisions to happen. Okay, now let's say, for example, let's explain this with an example. Activation energy for the reaction that we discussed above, A plus B reacting to form AB, the activation energy for this particular reaction is, let's say, 25 joules. If the particle A and B, let's say they have energy of 20 joules and 20 joules, now this energy is less than the activation energy. That is why when they collide with one another, they are going to bounce back because it's not crossing the activation energy threshold. Let's say now the particles, they have an energy of 30 joules and 30 joules. Now when the particles, they collide with one another, in this case they are going to form a new product. Yes, why? Because the energy, it is greater than the activation energy. So you need energy that is equal to activation energy or greater than activation energy for a successful reaction to happen. Right? Everything clear up till here?
Yeah. So it's like a successful collision. Would it mean like two particles in like the reactants? They have enough energy to collide, and then they form like a new sort of like particle. Like
Exactly. Yep. So in this case,
okay.
for example, this is an example of a successful collision, and this is an example of an unsuccessful collision. So successful collisions, activation energy, and a reaction happening, all of these things, they're interconnected with one another. If you have successful collision, that means the particles had enough energy, that means a new product will be formed or a reaction will take place. If there's unsuccessful collision, that means the particles did not have sufficient energy, and that means no new product is formed, and that means a reaction won't take place. Make sense now?
Yeah.
Okay.
Mhm.
Right. Now let's move on to the reaction profile diagrams. Okay, let's start with the reaction profile diagrams of an exothermic reaction. Exothermic reaction. Okay, in an exothermic reaction, again, what do we have? A and B, they are reacting with one another and they're forming AB. Now, one thing here is, as the reaction is progressing, the energy it's being given out, right? Because we're talking about an exothermic reaction. So let's say, for example, A and B, they had 25 joules of energy. As the reaction is moving from the reactants and it is forming products, energy is being released. That means the products is going to have less amount of energy, that is maybe 20 joules, right? So in an exothermic reaction, always remember the reactants, they have high energy, and relative to the reactants, the products, they're going to have low energy. This makes sense?
Yeah.
Okay. Now what we can do is we can sort of draw a graph. So let's say, for example, you draw the y-axis and you draw the x-axis. On the x-axis, we usually write down the progress of a reaction. And then on the y-axis, we have got energy as our label. First thing is, in an exothermic reaction, we need to show where the products and the reactants energies are lying relative to one another. So one thing that the reaction profile diagram shows you is it shows you the relative energies of reactants and products. Okay, so now in this case, we just discussed reactants will be present at a high energy level. So let's say at this point, and I can mark this as 25 joules. And the products, they will be present at a lower energy level. So let's say this is 20 joules right here. Right, and why are the products present on the right side and the reactants on the left side? Because as the reaction progresses, see how on the x-axis we have progress of a reaction, we are going from the reactants to the products. So we draw these two lines. This is reactants, this is products. Now we are going to join these two lines by sort of a bell-shaped graph or a curve like this. Now the question here is, why are we drawing a graph like this, and why is it not that we just join these two lines by a straight line like this? Why are we drawing a curve? Basically, the reason why we are drawing the curve is because of the activation energy. Let's say, for example, for this particular reaction, the activation energy is 30 joules. The particles that you have, A and B, that is 25 joules. What's going to happen is, and let's say this is a beaker, and in this beaker this reaction is taking place. You are going to heat the beaker. As you're heating the beaker, you're allowing the particles to gain more energy. So from 25 joules they go up to 26 joules, 27 joules, 28 joules, 29 joules, and then as soon as they reaches this threshold, which is 30 joules, now the reaction will be activated. The reaction does not start until and unless it crosses that activation energy point. So at 30 joules, it crosses the activation energy point, and that's when the exothermic element of it gets activated. So now energy is being released, and that is why you see this drop in the energy, and eventually you have the products in a reaction. right? So you're going from the reactants to the products, but then there's a part where the reactants have to give enough energy that they come close to activation energy or greater than the activation energy, and then the reaction starts losing energy because this is exothermic, and then eventually you have the products. Make sense?
Yeah.
Okay. Now, in a reaction profile diagrams, in the exams, they ask you to label two things. One of them is you have to label the activation energy. When you label the activation energy, you have to make sure you always draw it from the reactant level, an arrow from the reactant level to the peak of the curve. So like this. And then you're going to label this as activation energy. Activation energy, it has this symbol E and A. A stands for activation and E stands for energy. This is the activation energy, because remember, from 25 to 30, this was all the energy that it took to reach the activation energy point.
Okay.
Then the other thing that you usually need to label is the enthalpy change or the energy change that is present in this particular reaction. Now, enthalpy change or the energy change, how do we get that? We simply do the product's energy minus the reactant's energy. So, for example, in this case, product's energy minus the reactant's energy, product was 20, reactant was 25. The answer we are getting is negative 5. This negative 5, it basically shows us if your enthalpy change is in negative, that is an indication that this is an exothermic reaction, because it helps us understand that if the answer is in negative, that means the products have lower energy level than the reactants. And that is why when you label this enthalpy change on the graph, you label it as the difference from the reactant line to the product line, but you draw a downward graph because it shows us that there is a drop in energy and this is in negative. Is everything clear up till here?
Yeah.
Okay. Now, when we draw the same reaction profile diagram for an endothermic reaction, it's the same concept, it's just that the things, they're going to be opposite now. So, let's draw the axis again. We have progress of reaction on the x-axis, we have energy on the y-axis. Okay, again, A plus B forming AB. Now, if this is an endothermic reaction, do you think the product should have a higher energy level or a lower energy level compared to the reactants? What do you think?
Uh, Products would be have higher energy level if it's endothermic.
Perfect, exactly. So as the reaction progresses, energy is being absorbed. That means AB have high energy level compared to the reactants, so lower reactants have low energy level. So you do the same thing. Now reactants are going to be at lower energy level, products are going to be at a high energy level, and again you join these two lines by a bell-shaped graph like this. Okay, again, the same concept of activation energy applies here. So when you label the activation energy in the endothermic reaction, again, you are going to go from the reactant level to the peak of the curve like this, up till this point, and you're going to label this as the activation energy. And then what would be the enthalpy change? Again, the enthalpy change is going to be the difference between the reactants and the products. So a line drawn, an arrow drawn between the two. But now, since the enthalpy change will come out as positive, your arrow is also going to be upwards. So for example, if you are going products minus reactants, products have high energy level, 25 minus let's say 20, your answer will also come out as positive because the products have high energy level than the reactants. So again, if your enthalpy change is coming out as positive, that is an indication that the reaction is also endothermic.